I'm going to go through the example labeled 6.3.2 in the book to see when we would really need to use that formula for transforming or inverting an irreducible quadratic. So we start out by transforming both sides of the equation. On the right-hand side, we're going to get out the characteristic equation s squared plus s plus 1 times x, and then we're going to be subtracting out the initial condition times s minus the initial position times s minus the initial velocity. But since we're subtracting on the left, I'm going to add them all into the right-hand side. We're also going to be transforming this 3 sine of 2t, which gives us a 3 times the transformation of sine, which is 2 over s squared plus 2 squared. And, of course, I mentioned that we're going to be adding the initial condition. So from x prime, we add x sub 0 times the 1. Then from the x double prime, we add the x prime of 0, and then we add s times x sub 0. Now these components would be scaled by whatever coefficients we have in front of the x prime and x double prime, but it's simpler to write them all on the right-hand side because they are constants. We're plugging in the values of 1 and 0. Okay, so first off, let's solve for capital X, which is the transform of little x. So we get a 6 over s squared plus 4 divided by s squared plus s plus 1 plus, here's a 1 plus s, 1 plus s over s squared plus s plus 1. Now, it may be simpler to type this into your calculator or computer if you combine these together, because it's going to be a bit of work either way. So let's multiply top and bottom by s squared plus 4 to get common denominator, 6 plus s squared plus s cubed plus 4 plus 4s. And then combining terms, we have a highest power of s cubed, then an s squared, then a 4s plus a 10. Okay, so this requires partial fraction decomposition. And the book gives an example of using the Maple software using the expand command. Now, sometimes I think the expand command is also listed on a TI 89, so you're welcome to use that, or 90 or something like that. But I'm going to use WolframAlpha, and the command that we use in WolframAlpha is just partial fractions. And so let me slide over onto the computer screen here. I type in partial fractions, the command, and then I type in the rational expression. I have my s cubed plus s squared plus 4s plus 10 divided by my common denominator, and then I click enter, and it says, this is what I thought you said, and then here's the main result and a few other things in case you're interested in the plots. So that gives us all the coefficients we need to expand this out. For the s squared plus 4 term, we can write down the inverse very easily. But for the irreducible quadratic, we're going to use our formula. So back to the board. looking at this piece down the bottom, we know that C is equal to 1, D is equal to 1. So we compute A is equal to negative C over 2 equals negative 1/2. And then B is the square root of D minus A squared, which is square root of 1 minus 1/4, or square root of 3/4, which is square root of 3 over 2. So we have the exponential, the real part, but basically this A and B give us the real part and the non-real part of the eigenvalue, or roots, 1, 2, A plus or minus B I. That's what the A and B represent here. So we know that we have a damping of 1/2, so it's negative pulling down. And then the angular frequency is root 3 over 2. So that will control how frequently it's oscillating based upon the period. Okay, so let me clean this up a little bit. Erase the board a little bit, and we'll transform, using the formula, these two pieces. Okay, so now that we've used WolframAlpha or some other technology to expand, do the partial fraction decomposition, we can use our formula to translate this over. So first, we pull out the shift, which is e to the negative 1/2 t from this combination, and it's multiplied by the a 19 over, here, let's write up the formula first. E to the at times big A times the cosine of bt plus little a big A plus big B over little b times the sine of bt. So that's the expansion of the first piece. And then we have this other section, which is going to be minus, and we're going to look at a cosine piece, 6/13 cosine of 2t minus, and then we have the sine piece, and the sine piece, of course, needs a 2 on top. So I can think of that 18 as a 9 times 2, and 4 as a 2 squared. So we get a 9 over 13 sine 2t. Okay, so let's plug in what we know for these components. We have A and B defined. This right here is capital A, and this is capital B. Okay. So e to the negative 1/2 t times our 9/13 cosine of root 3 over 2t. So there's the cosine piece, plus we have little a times big A, so minus 1/2 times 19/13, so minus 19 over 26. 1/2 of that, so, and then plus 37 over 13, all divided by b, which is the square root 3 over 2. Whew. Okay, so that's the constant multiple of the sine piece, which is sine of root 3 over 2 times t. And then the same minus 6/13 cosine of 2t minus 9/13 sine of 2t. Whew. So that is how we can use both technology to expand out the partial fraction decomposition, but also a formula to translate an irreducible quadratic over. Now, I will finish up with simplifying this expression right here. But we're basically done. Let me just do some arithmetic here. Common denominator of 26. So I multiply the top by 2. That gives me a 60 plus 14 is a 74. I'm dividing by the square root of 3 over 2. It gives me let's see. Well, I'll take that square root of 3 over 2 in the bottom and just invert and multiply 2 over square root of 3. So that 2 will cancel with the 26's on the bottom to give us a 13 root 3 common denominator. And then I take my 74 and I subtract 19. Now that's, if I take 74 and I subtract 19, it's the same thing as taking 75 and minusing 20. Okay, so there's my arithmetic for you. We get 55 over 13 root 3, and then you plug it in. There we go. So now we've simplified down our expression for the underdamped component of it. This is the natural behavior of the spring in this system. And then we have the oscillatory particular solution. This is what will happen this is what will be left when time gets larger and larger. We can calculate how long it takes by seeing how long we get till we have a 4, negative 4 on top there. So t equals 8. So in about 8 units of time, the underdamped component will decay away to about 1 or 2%, and we'll only have the oscillations from the sine and cosine. We could then reduce these to find what the amplitude of that, you know what I did. We can go back and do all the things we did before by finding the amplitude of oscillation here. We're taking the square root of the sum of the squares. We can do lots of stuff with this. But let me just end with this point right now to say that the transformations we're doing are directly relatable to what we've been doing before. In most cases, we're looking for linear problems that have nice quadratic reductions. We looked at having factoring forms. We've looked at we can look at repeated factors. We can look at partial fraction decomposition for any combination of factors. But the problems we're solving are not that different than what we've done before. So our solutions should be not that different from what we've got before. And it makes sense. It's a good reality check.